Good morning, welcome to a new lecture. Today I will talk about virtual work method, or we call it principle of virtual displacement. Perhaps the most direct and comprehensive way in order to find deflection in the structure is virtual work method. This method is based on the virtual work displacement first formulated by John Bernoulli in 1717. John Bernoulli first formulated this method, and it is based on the principal work method, and he invented this. He was a Swiss mathematician, and this method is based on the energy method. The work in virtual work energy work method is energy required to move mass around in space. Or in simple words, if we have one box in one surface and we apply force P, if we increase this force P from 0 to a little bit, we will increase to a certain value, and that force is overcome to the friction force. Finally, what will happen? This mass will move in this surface, and we will have delta displacement. Here work is equal to P times delta. Of course, this is external work. External work, we apply force P. Because of that force P, we have displacement delta. So P times delta will give us the work. So the work in virtual work method is energy required to move mass around in space. Here P is the force we apply, delta is the deformation. If instead of force we apply moment, moment will cause rotation, so we can define work is equal to moment times rotation. So we know force will cause translation movement, so force times displacement is work. Moment will cause rotation, so moment times rotation again we will define as work. Let's look at to force respect to displacement plot. We increase the force until the certain value, then that force will overcome to the friction force, and we will have displacement for that box on this surface, flat surface. So here the area underneath of P delta plot, P times delta will be area underneath of this plot will give us the work. We can define work in another way. For example, If we have one spring, if we have one spring, I apply force F to this spring. This force F will cause displacement such as X. According to Hooke's law, we know F is equal K, the stiffness of the spring times X deformation. If we draw force respect to X plot, what we will have? Force respect to X. Here we apply force step by step. We increase from 0 to certain value. For example, first our force is 0, so displacement or elongation in the spring is equal to the 0. Then we increase force a little bit. For example, we increase force to the 10 pounds. Assume the deformation is 1 inch. So we will find another point. We increase the force to the 20 pounds. Deformation, for example, it is 2 inch and so on. If we attach these points, we will end up with one inclined straight line. And we know the slope of this line will give us the stiffness of the spring. We will show with K. Here, because we apply force gradually, our displacement increase gradually as well. Here, work is equal to force times displacement divided by 2. So work is equal to force times displacement divided by 2, or area underneath of this plot. Because it is triangle, here is the height is F, this side it is X. The area will be F times X divided by 2. This will give us again external work done by external force F. Instead of this spring, if we have a straight rod, we know rod is kind of spring as well. For example, we have rod here, straight rod. We apply force P to this rod. And you see, this is tension force. So we will have elongation. Elongation, assume it is delta. So in this straight rod, what is the external work? External work again will be P times delta divided by 2, because we increase this P from 0 and we increase step by step. So if I draw P respect to delta plot, first P is 0, so delta is 0. Then we increase P to the P1, delta will be delta 1. We increase P to the P2, delta will be delta 2. And we will have curve like this, one straight line. The area underneath of this will be area underneath of this triangle, and it will be P times delta divided by 2. Pay attention, we assume here our material, it is linear elastic material, and we are in small deformation range. In small deformation range, most material behavior, it is linear elastic, and they obeys Hooke's law. So we can write this. This external work, we apply this external work or energy. What will happen to this external work? We know, according to the conservation of energy law, we know from the physics law of conservation of energy. According to this law, what we know? We know the energy never will be created or destroyed. So if I want to write law of conservation of energy in simple word, I can write energy or work can never be created or destroyed. So according to the law of conservation of energy, energy or work can never be created or destroyed. So if we apply this external work, that external work will create internal work. That internal work, it will be energy, is stored in this system. In most structural member, energy is stored as a strain energy. So, in most structural member, if we apply external load, that external load will create internal load. That internal load will create internal stress. Internal stress will create internal strain, and that energy will be stored as a internal energy or internal strain energy in a system. For example, let's come back to this rod problem. Here this is P times delta over 2, which is our external work. This external work should go somewhere. It will be stored as a strain energy. What is strain energy here? Strain energy, usually they show with U, which is equal to internal work, is equal to stress times strain times the volume of that body or member divided by 2, because again for linear elastic material, stress-strain curve, it is linear. The area underneath of that will be sigma times epsilon over 2, because it's stored in entire volume of the body. We should multiply to the volume V. So let's look at here. What is the stress here in this member? Stress, we know it is equal to force divided by cross-sectional area. Strain, we know, is equal to elongation divided by initial length. If we have straight rod subjected to external load P, the elongation from Hooke's law we can prove it is P times L over EA divided by L will be equal to P over EA. If we plug these here, what we will have, instead of sigma stress, we can put P external load divided by cross-sectional area times strain. Instead of strain, which is elongation divided by initial length, we can put again P divided by EA. The volume for this rod, if the cross-sectional is A and the length is L, volume will be A times L divided by 2. From here, what we have P square L divided by 2EA. This will be our internal energy or internal work or strain energy is stored in this rod. What is the external work? External work, it is P times delta divided by 2 P times delta, it is P L over E A over 2. That will be equal to P squared L over 2 E A. You see, external work should be equal to internal work. So, for one system, for one structural system, deformable body, our external work done by external force should be equal to internal strain energy stored in the system. So, let's I write this here. So, for a deformable body, we can write external work should be equal to internal work. The principle of virtual work for deformable body says that the external virtual work must equal the internal virtual work. So I can write external virtual work should be equal to internal virtual work. W stand for work. V here virtual, E external, I internal. Or I can write entire or summation of virtual external forces times real external deflections should be equal to entire or summation of virtual internal forces times real internal deflections. Okay, from here, so we know virtual external forces times real external deflection should be equal to virtual internal forces times real internal deflection. Let's look at one simple example to see how we can apply this. Okay, assume we have one cantilever beam subjected to concentrated load at free end. Point A, point B, the length is L, Young modulus is E, and moment of inertia is I. What will happen if we apply force, concentrated force at point B? We will have deflection or deformation, and point B will transfer to the point B prime, and here we will have maximum deflection, I show with delta B. This is our real system. So we have real beam, we apply force, we have deflection. We want to find this delta B. This is real system. Let's look at this beam. If I apply here one virtual load, I show it P and this V. V stand for virtual. What will happen? Here we will have deformation because of this virtual load here, P and this V. What is there here? External virtual work. External virtual work here will be virtual external forces times real external deflections. So this will be equal to virtual external force means PV times real external deflection delta B. What will be internal virtual work? Internal virtual work will be virtual internal forces times real internal deflections. So this will be equal to, what is our internal forces? If we apply virtual force, that virtual force will create virtual internal forces. It will create, for example, virtual internal moment. Virtual internal moment, I will show it mv. That will be a function of x, because in any section, if I cut it, the distance of that section from the free end or point B is x, I will have mv x. That will be our virtual internal forces times, if we apply moment to one beam, that moment will produce curvature. That moment will create curvature. The curvature will be function of x again from free end. I show that curvature with phi curvature, real deflection, phi, this R for real x, because in any section, the section distance is x from free end, we have different mv and phi. For entire beam, this will be integration from 0 to L dx. So virtual internal forces will be mvx times real internal deflection. It is curvature phi rx times dx, because for one small element, the element is, length is dx. Moment here, internal virtual moment, effective on this element, it is mvx, and the curvature of this element, it is phi x. So if we multiply mvx times phi x dx for this element, and we integrate from 0 to L, we will have internal virtual work. According to conservation of energy law, we should put these two equal. If I put these two equal, let's see what we will have. If we put these two equal, external virtual work is equal to internal virtual work. From here, what was the external virtual work? It was PV times delta V is equal to integration of mvx phi rx dx from 0 to L. What is the curvature for one beam? Curvature is equal to 1 over radius of curvature. If I show with rho, we know from mechanics of deformable body is equal to m over EI. So instead of phi rx, I can put m rx divided by EI. This will be equal to integration of from 0 to L m virtual x times m real x over EI dx. From here, P virtual times delta V will be equal to integration of from 0 to L m Vx m Rx over EI dx. If I assume this virtual external load is equal to unit load, I show with 1. So if I plug instead of PV 1, what we will have, I can remove this from here because it is 1. 1 times delta B means delta B is equal integration from 0 to L. The moment because of this virtual or unit load times the moment because of the real load divided by EI times dx should give us delta B. Pay attention. For beam, we have deformation because of several internal forces. We have deformation because of the shear force, we have deformation because of the bending moment, we have deformation for axial force. But for beam, what is our axial force? Is 0. So deformation for axial force will be equal to the 0. Deformation for shear force in short beam, it is large number, we cannot neglect. But for long beam, deformation for shear forces, if we compare with deformation because of the bending moment, it is a small number. So we can neglect that term. So for beam, in most cases, not all cases, in most cases for one beam, deformation or deflection, we will have, it is because of the bending moment, because of the bending deformation. So we will neglect the shear deformation. But in short beam, later on I will explain, we cannot neglect the shear deformation. We should consider that. But for most beams, we will neglect that term, and the deformation or deflection for the beam will be deformation or deflection because of bending moment. Here, I prove the deformation because of the bending moment. Let's make a story short. Solve this beam using virtual work method. For example, we have cantilever beam. It means one end it is fixed support, another end is free. Is subjected to concentrated load at free end. The length is L, Young modulus E, moment of inertia is I. We want to find the maximum deflection or deflection at point B. What we will do, we want to find delta B. We will apply unit load at the point we want to find deformation. Here we want to find deformation at point B. We will apply unit load at point B. So, what will be internal moment here? If I have a beam, I apply unit load here. If I cut in the x distance, the internal moment, because of this virtual load mv at x distance, will be equal to, if I take moment respect to cut point, I will have mvx is equal to minus x. Then if I find internal moment in real beam because of this real force, if I cut in the x distance again, m real at x distance, again if I take moment respect to the cut point, I will have m real x will be equal to negative px. Now we know delta B is equal integration from 0 to L m r x m v x over ei times dx. From here I can write from 0 to L minus px minus x dx over ei. That is equal to integration from 0 to L px squared dx over ei. So if I integrate this, delta B will be equal to px cubed over 3 ei from 0 to L. From here, delta B will be equal to pl cubed over 3 ei. So, for one cantilever beam subjected to concentrated load at the end, at free end, the deflection delta B will be P L cubed over 3ei. Let's look at the next example. Assume we have again cantilever beam subjected to uniform distributed load. The intensity of the load, it is lowercase w, for example pound per feet. The length is L, Young modulus is E, moment of inertia is I. Point A, point B. We want to find delta B. Again, formula mRx, moment because of the real load times moment because of virtual load times Ex over Ei. Now here, if I cut in the X distance in real beam, what I have beam, the distance from point B is X. I cut it here, M real X. Here is subjected to uniform distributed load. The intensity of the load, it is lowercase w. So what will be mr x? If I take moment respect to cut point here, point O, that will be minus w x square over 2. Because I want to find deformation at point B, I apply virtual load at point B. Again, if I cut this beam in the X distance, here I have unit load 1, virtual load 1. The internal virtual moment, if I take moment respect to cut point O, I will have mvx is equal to negative x. Let's plug here. If I plug here, it will be integration from 0 to L minus w x square over 2 times negative x times Ex over Ei. That will be equal to integration from 0 to L w x cube over 2 Ei dx. If I integrate this, it will be w x to the power of 4 8 Ei from 0 to L. If I plug this, I will end up with w L to the power of 4 over 8 Ei. So, deflection at point B, because of this distributed uniform load. So if we have cantilever beam subjected to uniform distributed load, the deflection at point B, free end, will be equal to W, intensity of the uniform load, times L to the power of 4, L is length of the beam, over 8 Ei, E Young modulus, I moment of inertia respect to neutral axis. So, these are two examples I solved using virtual work method. Next session, I will solve several examples using this virtual work method. Virtual work method is easy to apply, the most comprehensive method. In most cases, we can apply and we can conduct calculation very fast. For these integrations, sometimes integration will be complicated a little bit, but don't worry. For those cases, somebody before integrated for most cases, and according to the moment diagram shape, they develop table. So we will look at to those tables, we will figure out the coefficient for integration. That I will explain later. For now, we will integrate, but in order to do calculation very fast, we will use those tables later on. Thank you so much for watching this lecture. See you next session. Bye bye.